Combinatorics, Lecture 10, Nonhomogeneous recurrence. We start by defining what kind of recurrence we will study during this lecture. Definition. A sequence A, which consists of the elements ai, where I is a non-negative integer, is given by a nonhomogeneous linear recurrence with constant coefficients, provided that there exists k, a positive integer, and complex numbers gamma 1, gamma 2, and so on, gamma k, and beta, where beta is different from 0, such that for all n greater than or equal to k, an is equal to gamma 1 an minus 1, plus gamma 2 an minus 2, plus and so on, plus gamma k an minus k, plus beta. So the difference with what we looked at during the previous lecture is this beta, which appears here as an additional summand. So for beta equal to 0, we obtain the usual linear recurrence with constant coefficients, the homogeneous one. For example, the sequence an is equal to n for n greater than or equal to 0 is given by the following non-homogeneous linear recurrence: an is equal to an minus 1 plus 1. So we can take k to be equal to 1 and gamma 1 and beta to be equal to 1, both. Let us remark that the last time we saw the same sequence an is equal to n, where n is greater than or equal to 0, given by a homogeneous recurrence but of order 2. So we can write that an is equal to 2 an minus 1 minus an minus 2 for all n greater than or equal to 2. So the same sequence can be given by a homogeneous recurrence and a non-homogeneous recurrence. Proposition. Let A and B be two sequences satisfying the same non-homogeneous linear recurrence with constant coefficients, where the parameters are k, gamma 1, and so on, gamma k, and beta. Then the difference A minus B, that's a new sequence, satisfies the homogeneous linear recurrence with constant coefficients and with parameters k, gamma 1, and so on, gamma k, and then there is no beta because the recurrence is homogeneous now. Proof. So since an satisfies our non-homogeneous recurrence, so an is equal to gamma 1 an minus 1 plus and so on plus gamma k an minus k plus beta. And similarly, bn is equal to gamma 1 bn minus 1 plus and so on plus gamma k bn minus k plus beta. If we subtract the latter from the former, we get that an minus bn is equal to gamma 1 an minus 1 minus bn minus 1, that's the difference between these two summands, plus and so on, plus gamma k an minus k minus bn minus k, and then beta cancels out. Consequently, if we know one sequence which satisfies our non-homogeneous linear recurrence, so a particular solution to this recurrence, then all other sequences, so the general solution to the non-homogeneous recurrence, can be obtained by adding to our particular solution sequences that satisfy homogeneous recurrence. So the general solution to a non-homogeneous recurrence equals a particular solution to the non-homogeneous recurrence plus a general solution to a homogeneous recurrence. And last time we saw how one can compute the general solution to a homogeneous recurrence. Here is an example. Let us compute a general formula for all sequences given by the non-homogeneous linear recurrence an is equal to an minus 1 plus 1 for all n greater than or equal to 1. We already know one solution. We know that the sequence bn is equal to n, where n greater than or equal to 0 satisfies this recurrence. So we have our particular solution. Now we look at the homogeneous recurrence. an is equal to an minus 1 for n greater than or equal to 1. The characteristic polynomial here is lambda minus 1. It has only one root, namely 1. Therefore, the general solution to the homogeneous recurrence looks as follows. So Cn is equal to alpha times 1 to the power n. 1 is the root of the characteristic polynomial, but 1 to the power n is 1 for any n, so it's just alpha, where alpha is a complex number. Therefore, the general solution to the non-homogeneous recurrence looks as follows. An is equal to n, that's our particular solution, plus alpha, alpha is some complex number, for all n greater than or equal to 0. Let us note that this alpha is exactly a0, so we can instead describe the sequence as an is equal to n plus a0 for all n greater than or equal to 1. Let's look at another example. Let us compute a general formula for all sequences given by the non-homogeneous linear recurrence an equals to 2 times an minus 1 plus 1 for n greater than or equal to 1. So we first look at the homogeneous recurrence. So the homogeneous version is an is equal to 2 an minus 1 for n greater than or equal to 1. The characteristic polynomial is lambda minus 2. It has one root, namely 2. Therefore, the general solution to the homogeneous recurrence is Cn equals to alpha times 2 to the power n for some alpha, where n is greater than or equal to 0. Now we need to find a particular solution for the non-homogeneous recurrence. Let us try to guess one. So let a0 to be equal to 0, and then our non-homogeneous linear recurrence gives us 0, then 2 times 0 plus 1 is 1, 2 times 1 plus 1 is 3, 2 times 3 plus 1 is 7, then 15, 31, and so on. And this looks very much like 2 to the power n minus 1. So 1 is 2 minus 1, 3 is 4 minus 1, 7 is 8 minus 1, and so on. So let us check that the sequence 2 to the power n minus 1 satisfies our non-homogeneous recurrence. So we need to check that an is equal to 2 an minus 1 plus 1, and where an is 2 to the power n minus 1. So we plug in on the left-hand side 2 to the power n minus 1, on the right-hand side 2 times 2 to the power n minus 1 minus 1, and then plus 1. And then we see that 2 to the power n cancels, and we have here minus 1, minus 2, plus 1. So this is indeed true. So we have a particular solution to our recurrence, which has the form 2 to the power n minus 1. Hence, the general solution to the non-homogeneous recurrence is an is equal to alpha times 2 to the power n plus 2 to the power n minus 1 for all n greater than or equal to 0. So if n is equal to 0, we see that 2 to the power 0 minus 1 disappears, and we just get alpha. So alpha is equal actually to a0, so we can write the sequence as an is equal to a0 plus 1 times 2 to the power n minus 1. And this is true for all n greater than or equal to 1. Now there is a very nice trick that sometimes non-homogeneous recurrence can be reduced to the homogeneous recurrence. Proposition. Let A be a sequence which satisfies the non-homogeneous linear recurrence with constant coefficients for parameters k, gamma 1, and so on, gamma k, beta. If the sum of all gamma i's is different from 1, then the sequence B, which is given by bi, is equal to ai minus beta divided by 1 minus the sum of all gamma i's. So this sequence satisfies the homogeneous linear recurrence with constant coefficients for parameters k, gamma 1, and so on, gamma k, and now there is no beta because the recurrence is homogeneous. Proof. Let us try to find a sequence of the form ai plus lambda, where lambda is a complex number. We denote the sequence by c, which satisfies the homogeneous recurrence. So what we want to do, we want to compute Cn minus gamma 1 Cn minus 1 minus and so on minus gamma k Cn minus k. So this is equal to, we plug in the expression for Ci, so it's equal to An minus gamma 1 An minus 1 minus and so on minus gamma k An minus k plus, and here we will get, because we have lambda, we will have 1 minus gamma 1 minus and so on minus gamma k lambda. Since we know that A satisfies a non-homogeneous recurrence, the collection of the first terms just gives beta, and so we get beta plus lambda times 1 minus the sum of all gammas. In particular, if lambda is given to minus beta divided by 1 minus the sum of all gammas, we obtain 0, which means exactly that C, for this particular lambda, satisfies the homogeneous recurrence. And that's exactly what we wanted to prove. Here's an example. Let us compute the general term of the sequence A, given by the recurrence an is equal to an minus 1 plus an minus 2 plus 1 for n greater than or equal to 2, with a0 equal to 0 and a1 equal to 1. So that's a Fibonacci recurrence, but now with some additional constant term. Note that 1 minus 1 minus 1 is not 0. So 1 is not the root of the characteristic polynomial. Therefore, the sequence B, which is given as follows, so Bn is equal to an minus 1 divided by 1 minus 1 minus 1, which is an plus 1. For n greater than or equal to 0, satisfy the homogeneous Fibonacci recurrence. Bn is equal to Bn minus 1 plus Bn minus 2. That's it. But now the initial conditions for B will be B0 is equal to 1 and B1 is equal to 2. From the previous lecture, we know the general solution to the Fibonacci sequence. So Bn is equal to alpha times 1 plus square root of 5 divided by 2 to the power n plus beta 1 minus square root of 5 divided by 2 to the power n. And now for n is equal to 0, our initial conditions, we get that alpha plus beta is equal to 1. For n is equal to 1, we obtain that alpha times 1 plus the square root of 5 divided by 2 plus beta times 1 minus the square root of 5 divided by 2 is equal to 2. We can solve this and obtain that alpha is equal to 3 plus the square root of 5 divided by 2 square roots of 5, and beta is equal to minus 3 plus the square root of 5 divided by 2 square roots of 5. So the general formula for Bn for n greater than or equal to 0 is as follows. 3 plus the square root of 5 divided by 2 square roots of 5 times 1 plus the square root of 5 divided by 2 to the power n plus minus 3 plus the square root of 5 divided by 2 square roots of 5 times 1 minus the square root of 5 divided by 2 to the power n. This is for the sequence B, and for the sequence A, which is B minus 1, we get the same formula, minus 1. And this gives us the general form of our sequence an for any n. Until this point, we considered recurrences which were linear, non-homogeneous, and with constant coefficients. Now we can generalize it a little bit and allow for the extra term, which we add, to be not necessarily constant. So let us consider a sequence A, which is given by the general non-homogeneous linear recurrence, in the sense that there exists a positive integer k, then constants gamma 1, gamma 2, and so on, gamma k, complex numbers, and the function f from positive integers to c, such that an is equal to gamma 1 an minus 1 plus gamma 2 an minus 2 plus and so on, plus gamma k an minus k plus f of n for all n greater than or equal to k. And of special interest for us will be the case where f is a polynomial function. We have the same structure theorem for such sequences as for non-homogeneous recurrences with constant coefficients. Proposition: if we have A and B, two sequences which satisfy the same non-homogeneous linear recurrence with parameters k, gamma 1, and so on, gamma k and f, then the difference between A and B satisfies the homogeneous recurrence with the same parameters when f disappears. And the proof is exactly the same as for linear non-homogeneous recurrence with constant coefficients. Consequently, in order to write a general formula for a non-homogeneous recurrence, one needs to find a particular solution. And as soon as we know such a solution, a general solution is this particular solution plus the general solution for the homogeneous recurrence, and that we know how to do from the previous lecture. And then, when we know the general solution to the non-homogeneous recurrence, we can determine the coefficients, which are variables in this solution, using the initial conditions of the sequence. So the big question is how to find a particular solution, and for this there are various tricks and techniques. And in our special case, when our function f is a polynomial of degree d, we can always try to look for a particular solution in the form of a polynomial in n. So that is, an, this particular solution, is of the form g of n, where g is some polynomial for all n greater than or equal to 0. But polynomials can have different degrees, so a good question is how to bound efficiently the degree of g. It turns out that the answer depends on the multiplicity m of the number 1 as a root of the characteristic polynomial of the homogeneous recursion. So it shouldn't be f of x here, it should be the characteristic polynomial of the homogeneous recursion. And the degree of g, which will work, will be d plus m. So d is a degree of f, and m is a multiplicity of 1 as a root of the characteristic polynomial. So in fact, there should be a particular solution of the form g of x is equal to x to the power m times c dx to the power d plus and so on plus c1x plus c0. Let's look at a couple of examples. Example 1. Consider the recurrence an is equal to 2an minus 1 plus n, and where a0 is equal to 0. The homogeneous recurrence is bn is equal to 2bn minus 1. The characteristic polynomial is x minus 2. 1 is not a root at all. So the general solution for the homogeneous recurrence is bn is equal to alpha times 2 to the power n, for all n. So we look for a particular solution as a polynomial of degree 1, so that's a degree of our f. 1 is not a root of the characteristic polynomial, so degree 1 should work. So we look in the form Cn is equal to beta n plus gamma. We insert this into our recurrence, and we get beta n plus gamma is equal to 2 times beta times n minus 1 plus gamma plus n. And this reduces to 1 plus beta n plus gamma minus 2 beta is equal to 0. And we see that here we can take beta is equal to minus 1 to kill this, and then gamma is equal to minus 2 to kill this. So Cn, which is equal to minus n minus 2, is a particular solution to the non-homogeneous recurrence. So the general solution to the non-homogeneous recurrence has the form an is equal to alpha times 2 to the power n minus n minus 2. For n equal to 0, this gives 0 is equal to alpha minus 2, and hence alpha is equal to 2. So the final answer is that an is equal to 2 to the power n plus 1 minus n minus 2. That's the general term of our sequence. Example 2. Consider the recurrence an is equal to an minus 1 plus n for a0 equal to 0. The corresponding homogeneous recurrence is bn is equal to bn minus 1. The characteristic polynomial is x minus 1, and here we see that 1 is the root of multiplicity 1. But the general solution to the homogeneous recurrence is bn is equal to alpha times 1 to the power n, but that's just 1. And 1 is the root of the characteristic polynomial of multiplicity 1. Let us first check that looking for the particular solution as polynomial of degree 1, which is the same as the degree of our term here, will not work. So let's look for a particular solution as Cn is equal to beta n plus gamma. If we insert this into our recurrence, we get beta n plus gamma is equal to beta times n minus 1 plus gamma plus n. And now we see that this reduces to n minus beta is equal to 0. And this we cannot solve, we cannot make the left-hand side 0 for any beta, because beta is a constant and n is a parameter, it depends on n. So this doesn't work. Looking for a particular solution as polynomial of degree 1 doesn't work. But let us look at the particular solution as polynomial of degree 2. So let's look for Cn in the form beta n squared plus gamma n. If we insert this into our recurrence, we get beta n squared plus gamma n is equal to beta n minus 1 squared plus gamma n minus 1 plus n. And this reduces to minus 2 beta plus 1 times n plus beta minus gamma is equal to 0, which we can solve, and we get that beta is equal to 1/2 and gamma is equal to 1/2. Therefore, Cn, which is equal to n times n plus 1 divided by 2, is a particular solution to our recurrence. So the general solution to the non-homogeneous recurrence has the form an is equal to alpha plus n times n plus 1 divided by 2. And for n equal to 0, we get that alpha is equal to 0 by the initial condition. And so the final answer is an is equal to n times n plus 1 divided by 2. So these numbers are called triangular numbers. Note that they are all integers, despite of the fact that they look like rational numbers. In fact, these are binomial coefficients n choose 2. And one geometric example, which is a very interesting example. Let us look at the very special geometric figure which is called Koch snowflake. So that's a fractal curve in R squared, and it is defined as a limit of the following iterative procedure. So we start with an equilateral triangle with side lengths 1. At each step of the iteration, we take a side of the previous iteration, divide it into 3 equal parts, and for the middle part, we build an equilateral triangle outwards. So here are the first 4 iterations of this procedure. So we start from the equilateral triangle, and then we divide the 3 sides into 3 equal parts, and for the middle parts build equilateral triangles outwards. We get this picture. And then we do the same thing with this picture, we get this picture. We do the same thing with this picture, we get this picture, and so on. So let us compute the limit lengths of this curve and the limit area which this curve bounds. For a non-negative integer n, denote by mn the number of sides after n iterations, denote by ln the length of the curve after n iterations, and denote by an the area bound by this curve after n iterations. The initial conditions are m0 is equal to 3, we start with a triangle, 3 sides, l0 is 3, each side was length 1, and a0 is the square root of 3 divided by 4, that the area of the equilateral triangle with side lengths 1. So at each step, one side of the current curve becomes 4 sides of the next curve, of the next iteration. So mn is equal to 4 times mn minus 1 for all n greater than or equal to 1. And so mn is equal to 3 times 4 to the power n for all n greater than or equal to 0. In fact, and here we see a homogeneous linear recurrence of order 1. So mn is very easy to determine. At each step, one side of the curve, which had lengths q, becomes 4 sides of new curve, and each of these 4 sides have lengths 1 divided by 3 times q. So this gives that one side of length q contributes 4 divided by 3 times q to the total length of the new curve. So ln is equal to 4 divided by 3 times ln minus 1 for all n. And this gives us that ln is equal to 3 times 4 divided by 3 to the power n for all n greater than or equal to 0. And here we again see a homogeneous linear recurrence of order 1. Let us note that if we take the limit of this length, so the limit when n goes to infinity of 3 times 4 divided by 3 to the power n, this is equal to infinity because 4 divided by 3 is strictly greater than 1. So taking power n pushes all this to infinity. So the length of the limiting curve is infinite. Now let us try to determine the area. So at each step of our iteration, the area an is obtained from an minus 1 by adding m sub n minus 1 equilateral triangles, each with side lengths 1 divided by 3 to the power n. So the total added area is 3 times 4 to the power n minus 1, that's mn minus 1, times the square root of 3 divided by 4, that's the area of the equilateral triangles with side lengths 1, but we have side lengths 1 divided by 3 to the power n, so we have to multiply with the square of this number, 1 divided by 3 to the power 2n. So that's the total area which we add at each step. And this means that an is equal to a sub n minus 1 plus, and then this product becomes 3 square root of 3 divided by 16 times 4 divided by 9 to the power n. Here we have a linear non-homogeneous recurrence, which we can try to solve. So the characteristic polynomial is x minus 1, so the general solution is just constant, so Bn is equal to alpha, which is a constant. Let us try to find a particular solution. Now here we don't have a polynomial term, we have a term which looks like something raised to power n. So let's try to find a solution in the form Cn is equal to beta times 4 divided by 9 to the power n. If we plug this into our recursion, we get beta times 4 divided by 9 to the power n is equal to beta times 4 divided by 9 to the power n minus 1 plus our term 3 square root of 3 divided by 16, 4 divided by 9 to the power n. And this we can solve and get that beta is equal to minus 4 divided by 5 times 3 square root of 3 divided by 16. And so the general solution for an is alpha minus 4 divided by 5 times 3 square root of 3 divided by 16 times 4 divided by 9 to the power n. For n is equal to 0, we get that a0 is equal to the square root of 3 divided by 4. And this gives us that alpha is equal to 2 times square root of 3 divided by 5. Consequently, the general formula for an, after n iterations, the area of the figure which we have, is 2 times the square root of 3 divided by 5 minus our correction term, 4 divided by 5 times 3 square root of 3 divided by 16 times 4 divided by 9 to the power n. And this is true for all n greater than or equal to 0. Now we can take the limit n goes to infinity, and we see here that 4 divided by 9, this is strictly smaller than 1, so if we take this to the power n, this will go to 0. So the second summand will just disappear, and the limiting area will be 2 the square root of 3 divided by 5. So here we have this Koch snowflake. It's a very funny geometric figure in R squared. That's a curve which has infinite lengths, but which bounds a finite area. So that's a very interesting example. Some additional problems and questions at the end. Problem question 1. Prove that for a polynomial f of degree d, and in the case when the multiplicity of 1 as a root of the characteristic polynomial of the recursion is equal to m, there is a particular solution for the non-homogeneous recursion of the form x to the power n times cdx to the power d plus and so on plus c1x plus c0. Problem question 2. Compute the general term of the sequence A given by the recurrence an is equal to an minus 1 plus an minus 2 plus 2 for n greater than or equal to 2, with a0 being 0 and a1 being 2. Problem question 3. Compute the general term of the sequence A given by the recurrence an is equal to 2 an minus 1 minus an minus 2 plus 1 for n greater than or equal to 2, with a0 being 0 and a1 being 2. Problem question 4. Compute the general term of the sequence A given by the recurrence an is equal to an minus 1 plus n squared for n greater than or equal to 1, with a0 being 1. And problem question 5. Define and analyze an analog of Koch snowflake based on squares instead of triangles. Thank you very much, and see you next time.